podcast is brought to you by LMU Munich.
For showing up this morning. And okay, so I hope you remember what we did on Thursday, where I explained to you the basic idea behind the ADS-CFT correspondence. And today I want to move on to gauge-gravity duality in the proper sense, where we generalize the ADS-CFT correspondence to systems which have less symmetry than in this original version. So as you remember, in the original ADS-CFT correspondence, we have this huge amount of symmetry. We have the conformal symmetry and this additional SO6 global symmetry. And one of the main reasons why ADS-CFT works so well is because there's such a huge amount of symmetry. And so towards the end of the last lecture, I explained to you that made the statement more concrete that the dynamics should correspond to each other in the two systems, in the gravity and ADS and in the field theory side. And I explained to you that there was a one-to-one map between operators in the field theory side and gravity fields in the ADS side. And this will also turn out to be very useful today and also for some of the lectures which you are going to hear next week. And the main point today is that I want to show you that when you generalize the ADS-CFT correspondence, you can actually make use of it to describe some strongly coupled systems which may also have some applications in the real world. I mean, of course, since I only have 90 minutes, I'm not really going to reach the very interesting examples, but I will give you some flavor of how this can work, and especially how we introduce finite temperature and also finite density into the ADS-CFT correspondence. And so if you remember, so we had these various levels of limits which you can take in the ADS-CFT correspondence. And in the third level, we actually reached the stage where the field theory was strongly coupled. And the strongly coupled field theory was mapped to a weakly coupled classical gravity. Now, this is actually quite useful because there are many strongly coupled interesting physical systems around. And once you have strong coupling, it's with traditional methods, it's often hard or often even impossible to describe the physics happening there because you can't do an expansion in the coupling constant. So normally, if you calculate some physical processes in a quantum field theory, you do perturbation theory, which means you expand in the coupling. But if the coupling is very large, you can't do that, and then often you can't do anything. And especially if you want to describe dynamical processes. Of course, there are theories such as lattice gauge theory around where you can also calculate a strong coupling, but there it's very hard to actually describe dynamics for particles moving in some medium or things like that. And here the ADS-CFT correspondence can be very useful because it offers a possibility to address these questions. And that's also why there was quite some interest in ADS-CFT from the phenomenological side. And I think also it's very nice because you can start from something in string theory and you arrive at something which you can really describe to really describe physical systems in nature. So one typical example being superconductivity. Okay, I mean, this is still a research area which is still developing, so there's still many open questions, and it's a relatively young field, but so far it turned out to be quite promising. And I want to give you some flavor of this today. Okay, so I hope you remember everything I just said, although I didn't write anything on the blackboard. But okay, to be more concrete, let me start by reminding you what we did last time. So we said that a strongly coupled quantum field theory is mapped to weakly coupled gravity on ADS5. So I showed you this example with the S5, but in principle you could also take more general examples. And so the idea was that the ADS space so this in 5 dimensions has an SO 4,2 symmetry. And it has a boundary. And so it is natural to assume that this quantum field theory, which also has the same symmetry, actually lives on this boundary. It is natural. So this has also the same symmetry. Lives on the boundary of ADS5. And then the boundary values of the supergravity fields may be viewed as sources for the field theory operators. Okay, so what does this mean? It means if you have some action describing your theory or some generating functional, and then you take functional derivatives with respect to these sources at different values and at different positions in space, for instance, then you actually get a two-point function. Okay, so that's the definition of a source. And then you can study the asymptotic behavior of the supergravity fields near the boundary. And so I introduced these Euclidean coordinates where this is the radial direction and these are the coordinates parallel to the boundary. And so you can show that near the boundary we have as follows. So delta was the conformal dimension of this operator O delta. And so there's one term which corresponds to a VEV for this operator and another term which corresponds to the source. So 4 is the dimension of the boundary, so that's why there's a 4 there. Okay, and so this relation turns out to be very useful, and then you can basically say that this generating functional corresponds to the integral over the boundary of this ADS space. And then you have these sources coupled to the relevant operators. And so if you take functional derivatives, then you get these correlation functions. Okay, and so the idea of ADS-CFT is that this field theoretical expression is actually given by the gravity action here in one dimension higher. Okay, that's how far we got at the end of last lecture. And so this is all about the original form of the ADS-CFT correspondence. And now we say, okay, if this works so well, I also mentioned last time that you can test this by calculating some particular correlation functions. And then the idea is, well, if this works so well for this very symmetric case, let's just assume it also works for less symmetric cases, and then see how far we get and what physics we can describe this way. Okay. Yeah.
Normally, defining field theory of a space-time, you say that the fields have contact with Mars, and they have a certain fall-off rate, so the boundary value is 0. So why can you pick here in the while we say that the boundary values of the subgravity fields act as sources, but immediately you will say that the boundary values on the ADS space should be 0, right?
No, it's okay. It's a little different because normally, in quantum field theory, you have, let's say, flat space and so on, and then for unitarity, you have the fields have to vanish to infinity. But here it's a little different because you have this curved space which has a boundary at a finite. It's not at infinity. It's just here in space. And it's curved. This space is curved. So it's due to these very special properties of ADS that the structure is different. So you can view this coupling as a kind of conformal structure on the boundary. It's also very important that you have this conformal symmetry for defining this. It's definitely different because the space has this negative curvature and there's a well-defined boundary. Okay, and these modes, as I remember, were called, the first mode is called the normalizable mode because Z0 just goes to 0 on the boundary, and the second mode is called the non-normalizable mode because it diverges on the boundary. But also, this is just a coordinate singularity there. The curvature is constant everywhere in the space. Okay, yeah? Yeah. Yeah.
But then it seems to me that you then take Z0 goes to 0, which means R goes to infinity.
No, we made a change of coordinates, which I didn't tell you. So because this Z0 is L squared over this R, which we had before. I changed the coordinates. So now the boundary is at the 0.
The boundary, that goes to 0, which means R goes to infinity.
Okay, so let's go one step. Oops, let's go one step back. So when we did this near horizon limit, there was one region which gives you, well, there's in the near horizon limit on one hand side you get the ADS 5 times S5, on the other hand you get flat space. But once you take this low energy limit, you zoom into the near horizon region. And you're kind of trapped in there. You cannot see this flat space anymore. It's another geometry. And once you're in this ADS 5 times S5, you can look what happens if you go near the boundary of the ADS space. It's a second step. So here, everything I'm telling you today is after the near horizon limit. So in the near horizon limit, we zoom into the near horizon region and we cannot escape it anymore. Okay, so we are at such low energies that we are confined in this ADS 5 times S5. And when we are in the ADS 5 times S5, then we can look what happens at the boundary of the space. That's the idea. Okay, so now the next step is to say, well, this works so nicely and we can do nice calculations of correlation functions and so on. But can we also now generalize this to describe our favored strongly coupled field theory by a generalization of this method? And then, of course, you pay a price, because if you say, let's assume it holds also more generally, not just for this very symmetric case, and already in the first case it was a conjecture, then it becomes now even more a conjecture that it should be true. But nevertheless, since there are so few methods you can address these questions, what happens in a strongly coupled field theory, you just say, okay, let's see if we get something sensible and if we can use this to make some predictions. So that's the philosophy. So there's a slight change of philosophy now compared to the other lectures. Beforehand, I was trying to convince you that this correspondence makes sense. But now we say, okay, let's take it for granted and see what we can do with it and generalize it. And, but of course, one should be aware that, there's a certain amount of assumption in this. And so the first step, what you can do to generalize this to describe realistic field theories, is to actually introduce a finite temperature. And this is done by considering a black hole in the anti-de Sitter space. So I think you heard already about black holes in anti-de Sitter space in the lectures by Roberto Emparan. So here we will also discuss the field theory side of this. So if we put this black hole into the ADS space, then we get a Hawking temperature, and the idea is now this Hawking temperature we can interpret as a field theory temperature in the dual field theory on the boundary. And so the next thing I want to convince you is that this is really a temperature in a quantum field theory. Okay. So the new chapter is gravity dual of finite temperature field theory. And so we use an ADS Schwarzschild black hole. Okay, so before I start, maybe I should give you a certain amount of literature where this was first found. So the first paper by Melasena on what we talked last time was in November 1997. And so this was the first proposal of ADS-CFT. And then for calculating the correlation functions, and this field operator map, which I introduced last time, this was in a paper by Gupsa, Livanov, and Polyakov in February of 1998. And now today, for the finite temperature, this was a paper by Witten in April of 1998. Okay, so just to give you an overview of the first papers, and then of course there's this review by 5 authors whose the first letters of their names you can arrange into this word, so that's why it's called the Magoo review. It's a little silly, but okay, fine. And that was written in 1999. So there's Maldacena here also, so you can find this easily. Okay, so let's turn to this finite temperature field theory. So we start with this ADS Schwarzschild black hole, and then we show the relation to thermal field theory using the Euclidean signature metric for this black hole. So we show Okay, so the metric looks like this. ds squared is r squared over L squared, so this L is the same as we had before, the ADS radius, and there's some function f of r, and now we have this Euclidean time called tau, and we have a 3-vector in position space. And here's our phi sphere. And this function f of r, so if it were a constant, we had ADS 5 times this 5, but now we have this other factor which introduces a horizon. And so RH is the location of the Schwarzschild horizon. Okay. Now, okay, so we want this metric to be Euclidean because usually a temperature corresponds to a Euclidean time. And then if we look at, so if we want a Euclidean signature, the prefactor of this term should be positive. Because if it becomes negative, then we introduce a negative sign. So if we want this to be positive, we have to be outside of this black hole. Okay, so at the Schwarzschild horizon, this factor vanishes, and we can't go inside the black hole if we use these coordinates. And so let me write this down. So the Euclidean metric is defined only outside the horizon. And now let's zoom in this area close to the horizon. So we want the space to be regular. And it will turn out that the space is regular at the horizon only if this variable is periodic. Okay? And this period you can then identify with the inverse temperature. And I'm going to show you how this works now. So what I'm going to show now is that it is regular at the horizon only if this Euclidean time is periodic and the period which is proportional to beta, which is 1 over the temperature, is then identified with the inverse temperature. So basically, the Hawking temperature of the black hole becomes the temperature of the field theory on the boundary. So that's the main message. Now let me show you how this works. Okay, let me show you how this works. So we consider the behavior of the metric near the Schwarzschild horizon. And so now look at this metric, and if we zoom close to RH, then our metric actually reduces to the following. We can rewrite it in such a way. Basically, so we expand in R minus RH. Okay. And now we can perform a change of variables, and then this may be rewritten as in the following form. Okay, so I introduce a variable rho squared, which is the same as R minus RH, which has to be positive. And then we get the following. Okay. So now, if you look at this, just formally, this becomes the metric of a plane in polar coordinates. Okay? So because we can take this as an angle, so this corresponds to the metric of a plane in polar coordinates. So a plane in polar coordinates looks like this: d rho squared plus rho squared d theta squared. So now if I compare this metric with that metric, I have to see that this here has to be a multiple of 2 pi. I mean, we don't want a cone, we want a plane. Okay, so if we go around the circle once, the period, we have to rub 2 pi. And that determines the period of this expression. So this corresponds to the metric of the plane if we identify theta being equal to tau 2R8 over L squared. So if we don't do that, then we get a conical singularity. So otherwise, there's a conical singularity. So it means there's a deficit angle. And then, so the space isn't regular at the Schwarzschild horizon. And so the periodicity of the theta translates into a periodicity of this tau. And so and the period is 2RH over L squared times beta is equal to 2 pi. And so the temperature is 1 over beta, and therefore we find the relation that the Schwarzschild horizon is related to the temperature in this way. Again, L is always our ADS radius because we are in an ADS Schwarzschild black hole. And so this result is important because it exactly reproduces the Hawking temperature of an ADS Schwarzschild black hole. Okay, so this is important. Okay, so now our ADS space, although we know we put this black hole in the middle, it still has a boundary. And so if we compactify the time in the bulk, it also will be compactified in the boundary. And so, yeah? Yeah.
Just reply equals C root, then I will get, still I require the regularization of that point, so I will get a different temperature. So I'm just...
I'm not sure I can see what you mean. I mean,
okay, I just rescale rule. By C, for example, I just let root pi equals C root.
But then you just make the circle bigger, but I mean, it still has to go round into pi. I mean, I don't think...
No. Because just the metric will be a little bit different. So...
okay, I'm pretty sure what I have written is correct. So we can discuss this maybe later, but... okay, I'm pretty sure this is the only way to make this really regular. I mean, you just have a metric in polar coordinates, and the only way you make this a plane is that if your angle goes around in 2 pi. Otherwise, you just get a deficit angle. This I'm pretty sure. And so if you identify this with the period, if you have your compactified circle, then you automatically get a temperature. And I want to say a little more now why you get a temperature from the field theory point of view. Okay, sorry. I have to get this blackboard from there. 1 second, let me just get this blackboard and then we can...
Why should we avoid singularity small?
Well, I mean, otherwise your space, I mean, has a really bad singularity, and I don't think you want it. I mean, what happens? Okay, if you fall into a black hole, the point is that you don't notice anything when you pass the Schwarzschild horizon. I mean, it just means if you are past the black hole horizon, you can't go back. But in the moment you are there, you don't notice anything. If you had a bad singularity there, I'm sure you would notice. Okay. I mean, okay, it's just a particular solution of supergravity, and it should better be smooth when you pass the Schwarzschild horizon.
So how do I show that the dual case theory has the same temperature?
Well, I'm about to explain it. Just let me wipe the board, and I will say this. Okay, so the main point is now, if we look at this from the field theory perspective, so on the boundary, so basically the structure in the bulk also translates to the boundary. On the boundary, we also have compactified Euclidean time in 4 dimensions. And this is exactly the definition of a finite temperature field theory, as I show now. And so, what's the simplest possibility of defining a finite temperature field theory is the following. It's you start with a standard quantum field theory, you Wick rotate the Euclidean space, signature, I should say. And then you compactify the imaginary time on a circle. So, I mean, this looks like I'm just repeating what I said before, but the point is now I just forget about all this ADS structure. I just talk about a field theory in 4 dimensions. And then it just turns out that everything we just did is exactly what you have to do to get a finite temperature field theory in 4-dimensional Euclidean space. So you compactify, and then this gives you the inverse temperature. Okay, so the words are exactly the same. Now, of course, if you do this in quantum field theory, what you actually consider is the partition function, which the partition function in statistical mechanics is formally the same as the generating functional in quantum field theory. And now you just have this Euclidean partition function, and you know from statistical mechanics it's given by the trace of v minus beta h, with h the Hamiltonian of your system. And now if you look at the book on quantum field theory and at finite temperature, if you evaluate this in a quantum field theory, then you actually find that you have to sum over periodic states. So it's a result from quantum field theory. And we just, with the construction I showed you, we reproduce this quantum field theory result. So this is how you evaluate this trace. And if you're in a field theory, the sum over states actually translate into a path integral, which is again over all beta periodic states. And then you have the Euclideanized action for your quantum field theory. Okay, so the geometric construction which I showed you gives exactly the same result as if you were in a quantum field theory in flat space. And that's why Witten was motivated to say our gravity, 5-dimensional gravity theory with this black hole in the Schwarzschild spacetime is dual to a field theory at finite temperature. Okay, so that's the main message of this first part of today's lecture. And so now we have a field theory with finite temperature, and so now we can do some thermodynamics with it. And so the first thing what we want to do is to actually calculate the free energy of the theory, which is something useful to do if you have a system at finite temperature.
I didn't understand how to exactly identify this beta with that.
Okay, I jumped various steps because I want to show you some other things as well today. But if you look at any book in quantum field theory and you want to evaluate the sum, then you get to sum over these beta periodic states. And so beta is your Euclidean time. So it's really one coordinate in your Euclidean space. And if that's periodic, it's wrapped on a circle. But here in the Schwarzschild geometry, we also get that one coordinate wrapped on a circle. And this is...
Asymptotically, I have different geometry. I don't have any GTT, those factors. So I have only... So
Asymptotically, you have R4.
Yeah, asymptotically, I have R4. So I don't have any factors like R minus RH, etc. asymptotically.
Yeah, I mean, if you take R to be very far away from the horizon, this factor just becomes 1. I mean, if R goes to infinity, the factor just becomes 1. Asymptotically, this ADS Schwarzschild black hole space looks just, again, like flat space of the boundary.
So here, identification I have to make is different.
No, it's the one coordinate of the boundary directions which is compactified on a circle in both cases. I start with this 5D metric. I take one of my Euclidean direction and compactify in a circle. And I go to the boundary and I get, in principle, R4, but the same direction is always still compactified on a circle. And it has the same period as if I was doing a finite temperature field theory in this boundary theory. That's the important step here. Okay, I need to wipe the board. So it's a kind of end of the first part for today's lecture, and now let me wipe the board and then go on. Okay, now before I enter the calculation of calculating the free energy, I'll just give you an outline of what I wanted to show you today, because I'm not quite sure I'm really going to reach the end, but such that you have an idea where we're actually heading. So goal. So now we can do thermodynamics in the finite temperature field theory. Okay, so then if we want to, so something I hopefully can explain towards the end of the lecture today, that you want to have a further generalization of ADS CFT where you introduce a finite density as well. Because so far we only have the so-called canonical ensemble in our finite temperature field theory. If we want to have a grand canonical ensemble, then we need a finite density. So this hopefully I can also explain to you today. And then of course you can really study thermodynamics in the system. And then the interesting thing is that you can then go and try to apply this to real world systems. And so next week you will have a lecture by Son from Seattle. And he's just going to do exactly this for you. So this is a kind of preparation to what he's going to do next week. And so here you can really use this theory at finite temperature and finite density. And you can apply it to a physical system, which is the so-called quark-gluon plasma. Okay, and so this is a new state of matter involving quarks and gluons, which you observe at particular accelerators, and it turns out that this is a strongly coupled system. And so it's very hard to study the system by any means, and using these ADS-CFT methods, you can really predict some properties of this quark-gluon plasma which seem to be in agreement with experiment. So that's very exciting, because we started with these string theory methods, and we end up with something which you can compare to a real measurement in a real experiment. So that's why it's exciting what I'm telling you today. And so a further application, which you can also attempt to do with a relatively new field, is to apply this to condensed matter systems. And in particular, here you can apply this to superfluids and superconductors. And again, so some of them, not all of them, of course, but some of them are strongly coupled. And there are no methods to really describe them with traditional field theory methods, so there's quite some excitement of maybe using these methods to learn something new about these strongly coupled superfluids and superconductors. And okay, I see how far I get today, but just keep this in mind. If you just pay this price or say, I accept that the ADS-CFT correspondence is also true for finite temperature and finite density, then you can really use it to compare it to experiments. And there are some striking examples where there's some agreement or nice predictions. And so this is certainly a very active area of research. Yeah? Yeah, I want to explain. Let me go on and hopefully I will get. Finite density means that you have a chemical potential and a number operator, and I'll show you how you get this. But first I wanted to show it to you. Okay, so this is the program. Let me see how far I managed to do today. But first I want to go back to the thermodynamics and finite temperature field theory, and I want to calculate the free energy for our system. If I'm done with that, the next step is to introduce the finite density. Okay, and then please keep in mind that there's these really nice applications for what we are doing. Okay, so let's go to our first point. Yeah. Good point. No, of course. If I introduce the finite temperature only, then locally it's still conformally invariant. But the finite density is going to break the conformal symmetry. Okay, so it means that the dilaton is still a constant, and still, if you look at any point in your space, the transformations are still preserved, although you rub this on a circle in your space. Okay. I should also, the other way I can phrase this is I introduce a scale if I introduce a temperature, so usually this breaks conformal symmetry. But since the scale is arbitrary, I have just one scale, I can take any value for the scale I want, and kind of I recover some conformal symmetry. So it's not really badly broken. Okay, but the density, that's definitely going to break the conformal symmetry. Okay. So, in the thermal field theory, so we have this generating functional given by the path integral. And so now if we do our saddle point approximation, which I mentioned in the first lecture, then we just replace this by the action at the saddle point. Okay. And so then we can calculate with this object. And in ADS-CFT now says we can identify this action with the gravitational action. So the conjecture says identify this action with the gravitational action. But then, since we have this curved space, so far I explained this for a scalar field, but in ADS-CFT you can also do this for the metric. Okay, so the ADS-CFT correspondence says that I can identify this field theory object with the gravitational action. So let me put an exclamation. So here I assume that ADS-CFT is true. Or, I mean, the statement of ADS-CFT put in a formula is saying this. And so here what I'm going to do is to look at the Euclidean action for the saddle point, but now I'm going to consider the metric. So of course in our supergravity theory there are also scalar fields, but I just don't consider them for now, for simplicity. Okay, so if we want to calculate the partition function of our finite temperature field theory, we have to evaluate the Euclidean gravitational action at the saddle point. And that's what I want to do now, and this will give us the free energy of the theory. Okay. Okay, so we need to evaluate gravitational action at the saddle point, and if we do that, then so we can calculate the free energy. So let me show you how this is done. So the gravitational action looks as follows. So first we have our standard Einstein-Hilbert action. Let's do it in general d dimensions. So it's the Euclidean signature. And so in d plus 1 dimension, so this is the gravitational coupling constant. Then we have the Ricci scalar, so this is the Einstein-Hilbert action, and then we have an additional term which comes from the cosmological constant. Since our space has a constant negative curvature, it looks like this. Okay, and then something I didn't explain to you, and I just mentioned it for completeness now, is that we also need some boundary terms, the so-called Gibbons-Hawking boundary term, which is required by some regularity at the boundary. So you have seen that the coordinates, there's a coordinate singularity at the boundary, and so to deal with this, some counter terms are necessary, and this leads to these boundary terms. It's somewhat technical, so I don't want to emphasize this too much now, but just for completeness, let me write this down. So this is when R goes to 0. And here we have the so-called extrinsic curvature K. And then there's a term 2 times d minus 1 over L squared. So this is called the extrinsic curvature. So which is given by, so this is the induced metric, this gamma, and then we have a normal vector. Okay, I'm just writing this for completeness. So that's the induced metric on the boundary, and that's a normal vector on the boundary. And this whole thing is called the Gibbons-Hawking boundary term. Okay, so now now we have to look for the saddle point. So the saddle point is a solution to the equation of motion. But we know already a solution to our equation of motion, which is just this ADS-Schwarzschild metric. Okay? And this is just the ADS-Schwarzschild metric. Yes?
How do the dimensions work out in the last term?
It doesn't work out. Okay, I would have to check. Maybe, I don't know, I'm not sure, maybe here there's another power, or maybe there's a typo somewhere, but I can't hear what he said, sorry?
What's the constant K before the expression?
That's the gravitational constant. Wait, I mean, I'm sorry. I should have looked this in. Well, okay, I should have provided you with more details. But I mean, for understanding what I just want to explain now, so this is just this is related to the Newton constant, but you derive it from the 10-dimensional axiom. So there's some further ingredients here. Yeah, I'm sorry if the dimensions don't work out, but okay, I would have to sit down and check it again. I mean. That could be the case, yeah, true. That's, yeah, I think you're right. Okay. Okay, you're much better than me at checking this. So, okay, the only thing I want to say, look at the Einstein-Hilbert term, and this term comes from the cosmological constant. And for regularity, there will be a boundary term. Okay, so that's all we need to know for now. I'm sorry if it's not all matching with the dimensions. Okay, but so what we can do is we can write down the equation of motion for this, which are going to be our Einstein equations, and then the saddle point will be as given by evaluating this action on a solution to the equation of motion. But we already know the solution to the equation of motion because it's going to be the Schwarzschild metric. Okay, and so here, for simplicity, we rescale, or to get some nice expression, we rescale the Schwarzschild metric a little bit to the form we used beforehand. So we extract a factor of L to the front. And so it's just a rescaling with L, basically. And so in this case, the Hawking temperature, by the same argument as given before, looks like this. And so now, okay, I just plug the solution into the equations of, I plug this solution into this action, and if I do this, so evaluate on the solution, and then we get the following expression. And so we get some volume factor. And so this volume is the volume associated with these x directions here. Okay. And this we can also rewrite in the following way. Okay, so of course a requirement of what we consider is that that we have to stay in the regime of classical gravity, and this means our curvature has to be small. So the space-time needs to be weakly curved. And this means that L to the d minus 1 over this gravitational constant needs to be small. And now, since we remember from last time that we had this relation between the ADS radius and the parameters of the supergravity theory, okay, using this relation, then we find that this implies that n has to be large, n has to go to infinity. So we have this theory where only the planar Feynman diagrams survive. Okay, but now if we have this result, we can calculate the free energy and the entropy. Okay, before I wipe away these applications, please remember them. I mean, that's what everything I'm telling you today is heading towards, and that's why these calculations are interesting. Okay, so I'm going to wipe this off, but remember that this is a very active area of research, and certainly about the quark-gluon plasma you will hear a lot next week in the lectures.
After regularizing the section, so this on-shed action you have written.
Yes, okay, yeah, I'm not going to show you the details of the calculation, but
Background suppression or something.
well, okay, you have to introduce a cutoff near the boundary, so that you just go an epsilon away from the boundary, and then you do your calculation, and then at the end of the calculation you take epsilon to 0. So it's quite involved, and I'm brushing over all these details now, but you're absolutely right, yeah. Okay, so if we have the action, we can evaluate the partition function, and if we have the partition function, we can evaluate the free energy and the entropy. So that's by the standard thermodynamical relations. So I hope you remember this. So the free energy is minus T ln Z. And so this is going to be T times the Euclidean action evaluated at our saddle point. And so if I plug this in, I get minus 4 pi to the D, L to the D minus 1. Again, this volume factor, T to the D, divided by 2 K squared D to the D. And the entropy, so this is the free energy, and the entropy S is minus dF by dt. And so if I calculate this, I get 4 pi to the D, L to the D minus 1, and then there's this volume factor again, T to the D minus 1 over 2 K squared D to the D minus 1. And so we find that this expression for the entropy is exactly that what you expect if you look at the event horizon. And so we recover this relation between the entropy and the area of the horizon, which you know from black holes. So this is a consistency check. The expression for the entropy is equal to the area of the event horizon divided by 4 times the Newton constant, and the Newton constant is related to this kappa squared in this way. Okay, and this area entropy relation is universal for event horizons. Okay, so we get what we expect for the black hole, so which is nice. Okay, so what you should remember from this is that using this approach, I can define the thermodynamics for the finite temperature field theory, and I can calculate the free energy and the entropy. And now, so we go to the next step on the list, which is we want to also introduce a finite density. And before we introduce a finite density in ADS-CFT, I first have to tell you how you actually introduce a finite density in a quantum field theory first. So these first analyses won't have anything to do with ADS-CFT. This will be the second step. Okay, so first we consider a quantum field theory with a gauge symmetry and a scalar and a fermion charged under this gauge symmetry. Okay, so we have a Lagrangian for our quantum field theory. And this will look like this. So we have a covariant, gauge covariant derivative. Okay, so for simplicity, let me just take a U1 gauge symmetry. And then this is my kinetic term for the scalars. And then I have a kinetic term for the fermions. And then I have a gauge kinetic term. Okay, so now in this theory we want to have a finite density. So how is this achieved? Mm-hmm.
This metric,
Yes.
solution Lagrange, how we can see the RG flow?
The RG flow.
Yes, what's the metric for ADS flow sheet? Is this metric can?
Well, there is no RG flow because the theory is still conformal in a weak sense. I mean, okay, there is a scale given by the temperature, but it's still a conformal field theory. So the beta function is still 0. There is no flow.
Yeah, temperature.
Yes, okay. It's a conformal field theory where we switch on the temperature, but this doesn't generate a beta function. Okay, so it's a very special finite temperature field theory. It's an important point, but okay. We still have a conformal symmetry here in this system. But I'm going to break it now if I introduce this finite density. But so far there is no RG flow. Okay, you can also consider RG flows in ADS-CFT, but this is a totally different topic from what I'm talking about today. You can also deform the metric in a much more severe way than what I did today. Today I just looked at this Schwarzschild black hole. But if you really, you can also consider some relevant deformation where you switch on a running dilaton and then you get a beta function and confinement and all these things. But this is also possible, but it's another topic than what I'm talking about today. This would also be very nice to talk about, so you have to come back some other time. Yes? No, the physical importance of this result is that I can calculate the entropy for a finite temperature quantum field theory by using these gravity methods. Okay, that's important. I don't want to make a statement about black holes. Everything is known about the black holes. I want to make a statement about the quantum field theory. Well, I mean, if I use a black hole to calculate an entropy for a field theory, then the result should be consistent with the entropy of the black hole. Otherwise, something would be wrong. So, I mean, it should better be that I get the result expected from the black hole. But, I mean, as you can see, I really used ADS-CFT in the calculation, but I have a consistent result. Yes.
You have identified it. How can we ensure that this entropy is the entropy of the whole CFT? Because we don't know the CFT, what the CFT is.
Okay, that's a very good question. Okay, I didn't tell you really enough details to fully understand, but okay, so far I haven't done really very much. So I took this ADS space where I know the dual field theory is NX24 super Young-Mills theory. And then I put this black hole, so I introduced a finite temperature, which breaks the supersymmetry in some way. But I still know that the field content of my theory is the same as in this NX24 super Young-Mills theory. Okay, so now I've shown you the calculation in d dimensions because it works in d dimensions, but if I really want to write down a Lagrangian for the field theory, I should go to 4 dimensions again. That's a very good point. I mean, so far I made this big point to say we have this gravity theory and we have the quantum field theory, and for the quantum field theory we know exactly what it is. We can write down a Lagrangian, it's NX4 super Young-Mills theory. But many people now just constructed some toy models where they also say they go to one dimension lower, so they study three-dimensional field theories. And they say, let's apply exactly the same techniques, but in the 3 dimensions you don't know what a Lagrangian is. You can't write it down. And you just say, I know it's a certain quantum field theory with certain symmetries, and that's enough for what I want to study. But if you really want to say what the field theory is, at least in this example, you have to go to 4 dimensions. It's not entirely true what I said. I mean, in some examples, if I didn't start with D3 branes, if I started with M2 branes, then I could also tell you the Lagrangian in 3 dimensions. But yeah, this is an important point. Yeah. Yeah? Field theory, yes. Yes. Yes, it's a good question. If we calculated the same entropy in NX24 recoupling, this is an excellent question. I should have prepared this for the lecture, but unfortunately I didn't. But okay, a very good question. So, I mean, if we did the same calculation in the free theory, okay, I have to look it up. I mean, but I mean, you're right. I mean, one should compare to the result in what you get in NX24 theory at finite temperature. I mean, here we just see now it's a very economical way of calculating this. Very good question.
One small thing. When we do this finite temperature, and we want our partition function to be somehow convergent.
Yes.
We require this Euclidean action to be bounded from below.
The gravity action.
Yes.
Yes.
And I think it's possible to show that not bounded from below, in some sense.
Well, again, I think you have to be careful because it's in the ADS space and there's a boundary, and it is different from the free from the flat
in
space.
Normal gravity, I know that this is a problem because this Euclidean action doesn't work in classical quantum gravity.
Yeah, but this is just classical gravity. I'm not saying anything about. I mean, this is the good thing because if I take this particular limit of the ADS-CFT correspondence, I'm just talking about classical gravity. And I don't have to worry about all these quantum effects. But okay, this is totally right. I mean, if we wanted to go beyond this limit of n being infinite,
yeah,
then we have.
When I'm introducing this partition function, I want to be convergent in some sense, and I'm putting there some action which is not bounded from below, so it's not convergent, I think, or I don't know. I don't know. Maybe in ADS it's some miracle work.
I think to really answer your question, one would have to do exactly this calculation to see exactly what happens if you take your Schwarzschild metric and insert into this action. And I'm sure, I mean, you know, I'm sure what I'm telling you is correct. If you just take this action and plug it, if you take this metric, plug it into the action, you get a finite result. Nevertheless, I mean, I should say, I mean, there are some regularization issues, but that's more related because the coordinate diverges at the boundary. But it's not a curvature singularity, it's just a coordinate singularity. So very often in ADS-CFT calculations, what you will see that people introduce a cut of epsilon. So you don't look at the boundary, you go an epsilon away. And then you do the calculation. And then at the end, there's some counter terms which you have to subtract before taking the limit epsilon goes to 0. That's certainly a very important issue, but it's a little beyond the scope what I want to explain today. But it's a very good question, and if you're interested in this, okay, maybe I should say another very nice way of testing the ADS-CFT correspondence is to calculate the so-called conformal anomaly. And maybe if you're interested, and there you can really see how you perform this regularization. Okay, let me write some authors. So the first people who did this were Skandiris and Henningsen in '98. And so there's some regularization which has to be performed near the boundary. So you take an epsilon away from the boundary and then it goes to, you go to 0. I hope you can read this. So there is some subtle issue with regularization. And so here this is the first time where it appeared, but there is some consistent way of dealing with this. Okay, let me go back to the density. Okay, I was just going to clean this water. Okay. Okay, so let me just introduce this chemical potential. So we have this covariant derivative. And now what we do, we will break Lorentz invariance in a particular way. So the time component a non-vanishing expectation value. So we take the expectation value of a mu to be mu. And so this means that our gauge field will be equal to this expectation value and plus some fluctuation. So 0 refers to the time component. Now, if we do that, then we generate a potential. So let's take this ansatz and plug into this Lagrangian, and this generates a potential. So we have minus mu squared minus mu times psi dagger. So here this is an upside down mass term. So this generates an instability. Okay, and this is interesting because if you want to see condensation process like the formation of a superfluid or a superconductor, then you need an instability in your system. And here you can see how it appears in the field theory. But this operator here, okay, so what is psi bar psi? It's a number density operator, okay? So basically what we see, so that this term is of the form minus mu times n. And this you should know from your course on thermodynamics. So it means we have a chemical potential and a number density operator. Okay, so we create a grand canonical ensemble in doing this. So this means we can interpret this term as a chemical potential. Okay, and then we obtain a so-called Gibbs free energy. Omega, which is energy minus temperature times entropy minus mu times n. Okay, and okay, so now we can how do we realize this in gauge gravity duality? And so obviously, to get something in gauge gravity duality, we have to have a charge. We have to have this U1 gauge field, and so this means we have to consider a charged black hole then. And so the charged black hole is the so-called Reissner-Nordström. Black hole. So then in the gravity side, we will have a metric and a U1 gauge field. And so in addition to the Einstein-Hilbert term, we will also have a gauge kinetic term in our gravity action. And then the equation of motion, which are the Einstein equation. They will look like this. So R is the Ricci scalar. And so this involves the gravitational coupling and this gauge coupling for this U1. And so now we have some matter sector here appearing on the right-hand side of the Einstein equations. Okay. And now, if we want to have a finite density, we have to find a solution to these equations where the time component of the gauge field is non-zero. Okay, so, and I'll just show you such a solution. Okay, so this is the last thing I want to do. I show you the solution. So which is this Reisner-Nordström ADS black hole. And so let me just quickly write it down for you. Okay. So also this will be now in Minkowski signature. And okay, maybe this is hints to something which will be happening next week. So far I introduced thermodynamics in Euclidean space, which means that we are always in equilibrium situation. But next week you will also see dynamical processes, and then you need a time in addition to a temperature, and this is achieved by doing something like this in Minkowski signature. So let me leave this as a comment for what's going to happen next week. And so here is our 5-dimensional Reisner-Nordström black hole. And now this function f of r is going to look a little more complicated than for the Schwarzschild case. Because we also have a contribution from the density. I'll explain the symbols in 1 second. So this gamma is equal to the coupling strength. So and the important thing is now that we have this gauge field. And so it's time component, so I can also write this with t or 0 as I did before. And it's going to look like this. So I have a leading and a subleading term. And according to the rules of ADS-CFT, one corresponds to a VEV and the other to a source of an operator. So we have a VEV here and a source. And so the VEV, this corresponds to the chemical potential. Maybe I just got it the wrong way around now, I think. Okay, let me write this in an extra line. I'm sorry. Okay, this term contains a VEV and a source. And one of them will be the density, and the other one will be the chemical potential. Okay, I'm sorry, I should have made more closely the link to this formula, but it all works out. I just don't see it right now. But never mind. Okay, let me just conclude and tell you the main point of what we did. So we generalized the gauge gravity duality to finite temperature and density. And this means you can study the phase diagram, and so there will be very nice applications. To strongly coupled systems. And you can even think of comparing them to systems in the real world, like the quark-gluon plasma. Or superconductors. Okay. Okay, and I hope you see how the logic goes. So first we derive the correspondence with a maximum of symmetry being around. And then in the next step, we say, okay, we have this really nice relation where we can map a strongly coupled field theory to a gravity theory. Now let's do that with other examples of strongly coupled field theories, which are closer to physical applications. And there's a lot of applications, and this is certainly a very active area of research. And so I'm very happy you came to hear about this morning, and thanks for listening anyway, and good continuation next week, and I hope you will stay interested in gauge gravity duality. Thank you very much.